what is a polynomial? Hopefully you have some idea. You remember something from grade 9, 10, and 11 math. Polynomials are equations or functions that look something like this. Now, how do we know that's a polynomial? That's sort of what this lesson is about, and about some terminology surrounding that. So let's zoom back out here and see what we have. So polynomial equations, and we're actually using this terminology, f of x, to represent these. And when we do that, we're actually calling them functions. And we know polynomial equations are actually functions. So I'm just going to change that actually to functions. And remember what functions are. Functions are basically things that pass that vertical line test, right? There's only one y value for each x value. So we assume all polynomials are functions, which is why we can use that f of x terminology. So the degree, first of all, the degree of a polynomial, we call that n in this course. And we can see in our general case, or any polynomial in general, we have ax to the n, and that's just our highest exponent. The leading coefficient a is basically the thing that comes in front, the number that comes in front of that variable with the highest exponent. We call that the leading term, and in front of the leading term is the leading coefficient, which in this case is a. So if we go to our example over here, on the other side, what's the degree of this function? Well, it's the highest power, the highest exponent, which in this case is 3. What's the leading coefficient? It's just the number that comes in front of that term. And in this case, it's 3. Well, is it? Can't forget about that negative. It's actually negative 3, right? Because we see that down here. It's negative 3, not just 3. So here we have a bit of a checklist to check to see if something is a polynomial or not. For something to be a polynomial, the leading coefficient needs to be a real number, so just a number in general. The exponents have to be positive whole numbers. And the equation can be written explicitly in terms of one variable, so y equals or f of x, as we like to say. So keeping that checklist at the top there, let's see if these equations here are polynomials. So let's look at the first one, f of x, function f. Is it a polynomial? Actually, you know what? Pause the video right here. This is what we're going to do. We're going to pause the video right here. I want you to try to fill out this whole table yourself. So take 5 minutes, answer the whole thing, then you can unpause and we will take it up. Okay, so pause. All right, hopefully you've tried out the questions yourself. So now let's take it up. First one, is it a polynomial? Well, let's look at the checklist. Does it have a leading coefficient that's a real number? Let's look. What's our leading coefficient? Well, it's the thing with the highest power. It's the thing in front of that. So our leading coefficient, as part of our leading term, is going to be 3, right? What's our degree, or the highest power? That's going to be 2. I mean, it's quadratic, right? So is it polynomial? I think so, right? It satisfies all 3 of those things above. Second one, is that a polynomial? Let's look. Exponents, we have an exponent of 1 in the first one that we can't see, 7 in the second one, 4 in the third one. So all the exponents are whole numbers. So yeah, we can say basically that it's a polynomial, right? So it's going to be a polynomial. The degree is the highest power, which is 7, and then attached to that 7, x to the 7, is a 5. So the leading coefficient is 5. Next one. Let's look at this one. We have an exponent of 3, 2, 1, and then the 2 here, we can say that has an exponent of 0, basically, and then we have an exponent of negative 1. So does this satisfy all our conditions? Exponents are positive whole numbers. See, we have a negative exponent, and when we have a negative exponent, it's actually not a polynomial anymore. It turns into some sort of reciprocal function, or a combination between a polynomial and a reciprocal function. And if you throw that into Desmos or other graphing software, you can see that it doesn't end up looking much like a polynomial at all. So anyways, is it polynomial? No, it's not. Right? So we don't have to worry about the degree or the leading coefficient when it's not a polynomial. Next one, I. 3x cubed plus 4x to the 2.5. Again, that same condition. Exponents are positive whole numbers. The exponent's not a whole number. we end up getting something silly in that exponent. So it's not, if you graph this, you would see it doesn't actually look like a polynomial. It looks like something else. So it's not a polynomial, so we don't need to worry about the degree and the leading coefficient. What about this one? This one's sort of obvious. If you break it down, it doesn't look like a polynomial, right? Because it's got a big fraction. If you break it down, you see that the top part, though, is a polynomial, and the bottom part is also a polynomial. Just together, they're obviously not a polynomial. They make what's called a reciprocal function, or a rational function, I should say. So it's not a polynomial, and we can't do that part. Last one, k of x. Polynomial or not? Well, let's look at our exponents. 3, 5, and that 4 has an exponent of 0, basically, x to the 0. Is that a polynomial? Well, let's look at our checklist. The leading coefficient is a real number. Is it a real number? What's the leading coefficient, first of all? Looks like it's attached to this one, -3. Right? What's the degree? Is the highest power, which is 5. And that 2/5 at the beginning, is that going to complicate things for us? And the answer is no, not really, because our coefficients are allowed to be decimals or negative numbers, just not our exponents. So it actually is a polynomial. And again, if you threw it into graphing software, you'd see that it ends up being a polynomial. Okay, now that we've reviewed equations, let's look at some graphing characteristics of polynomials. So first of all, what's a turning point? We have a polynomial here. What's a turning point? Think about it this way. If you're following the path of that polynomial, when do you have to change direction? So we're sort of going down, 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 down. And then maybe here, we're going to have to end up going up, 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 up. So there's a turning point here because we have to change direction. And same thing here. We have to go from up to down, right? So that's going to be a turning point here. And then from here, we have to go from down to up. So that's going to be another turning point here. I'm going to call those turning points TP, just for short, as turning points. Okay, so we have, we have a turning point there, we have a turning point there, and we have a turning point there. So those are our turning points of our equation. Next, we're looking for the global maximum and the global minimum. And exactly as it says, the global maximum is just where the graph, the highest point the graph reaches. Well, we're only shown a part of the graph here, up to about a value of 3. But what's missing from this graph, actually, I should have added this in, are little arrows on the end, because we know this graph is going to keep on going forever, just like a parabola will keep on going forever, right? So our global maximum, the highest value this graph is reaching, these things are going to just keep on going up forever. So we can see our global maximum essentially is going to be infinity, positive infinity, right? Goes up, keeps on going up. What's the global minimum of this function? Well, that's going to be the lowest point this function reaches, and it looks sort of like it's something like that, right? The lowest point. I'm just going to approximate because it's not on an equal value. It looks something like, I don't know, 0.75, 0.8. I'm going to put 0.8. And we can label those things, the local, so local and global are two different terms, right? Global refers to the highest point and the lowest point the graph reaches. Local maximum minimum values refer to the maximum minimum values if you're just looking at a small part of the graph. So for example, we're just going to zoom in here. If I'm looking at this part of the graph, right, just this part of the graph, this looks like it's a minimum here. So we would call that a local min, right, or local minimum, because it's in that region, it's the lowest point on the graph. It also happens to be the global minimum, but that doesn't matter. It's also a local minimum. If we go to the next point here, the next turning point, is this a local minimum or local maximum? Well, if we're looking at just this part of the graph, this is going to end up being a maximum, right? It's the highest point in that little section. So we call this a local max. And then lastly, if we go to this last turning point here, if we look at just this little segment here, this, again, it looks like a minimum. So we're going to call it a local minimum. Sort of like if you zoom in on any polynomial function enough, you see it ends up looking sort of like a quadratic, and we can just look at it that way for the minimum and maximum values. And then the last thing we're asked to find for this is the zeros of the graph. And we should remember the zeros are where the graph crosses the y-axis, right? So, or sorry, the x-axis. So this is the x-axis here. This is the y-axis here, obviously. So the points at which the graph touches or crosses the x-axis are going to be, if we zoom in here, right here, right here, and right here. So we have 3 zeros for this function. And I'm actually just going to state the values here. So the zeros are going to occur at -2, -1, and 1. So those are the zeros of the function. So here we have the last little part here, the last way we can identify a polynomial, and it's by the finite differences. And we know this, the first differences, second differences, that's essentially all we're talking about here, the differences between the values. So we're asked to determine, basically calculate the differences of the table below. So first of all, you need to use you need to plug in the values to generate the y values. So I'm going to do that now. Do it yourself. You can pause it here, do that, and then come back in a second. So this is what you should get if you do it. Those are your values. Now, before we calculate the differences, what degree is this function? If we look at it, the leading coefficient is going to be 2, the highest power is going to be 3, so this actually, we know it's going to be a third degree polynomial. Let's see how the finite differences show us that. So remember, how do we calculate the finite differences? We're basically looking for how the numbers change as we go down, right? So how does the number change when we go from that? And we could just do that by subtracting the bottom one minus the one above it. So -24 minus -24 minus -62 is 38. So it's actually positive 38, goes up by 38. Next one, 24 to -10. Oh, I can do that one in my head. That one goes up by 14. What does it go? What's the difference here? It's going to go up by 2, right? This one, well, it's going from -8 to -6. So it's also going up by 2. And then this one here, it's going from -6 to 8. So we are going up by 8 plus 6 is 14. Okay, that's cool. So no pattern yet. There's just sort of look like random numbers. So let's find the second differences. How do these numbers change now? We can do 14 minus 38, which is -24. So we're going to go down by 24 to do that. From 14 to 2, I can do that one. That's -12. Then we go from 2 to 2, so we're not changing at all. That's 0. And we go from 2 to 14, so we're going to go up by 12. Okay. Interesting. So we still don't have a pattern, but you can maybe identify what the pattern is going to be. If we do the third differences, going from -24 to -12, we've increased by 12. Then here we're going to also increase by 12. And then here we're also increasing by 12. So what do you notice? We have our first differences, we have our second differences, and we have our third differences. What do you notice about the third differences? They are all the same. And when those third differences are all the same, that means the degree of the polynomial is going to be 3. So whichever differences are the same, that means the function is going to have that degree. So just to sort of summarize this on the side, if a polynomial has degree n, its nth differences should be the same. Okay. So we should be able to identify the degree of a polynomial just by finding its differences. So last example, there's no equation given for this one, we're just given the x and the y values. So what I want you to do now is pause the video, try to identify the degree of the polynomial yourself, okay? And then unpause it and we'll go through the solution. So there's our differences. So we'll notice these are the first differences and these are the second differences. What do you notice? Well, the second differences are the same, so what must the degree of the polynomial be? The answer is 2. Sort of a boring example, but that's the answer. So let's write that. The degree, so therefore, so I'm just going to actually write the whole thing, because the second differences are the same, therefore, the polynomial must be degree 2. Is degree. So that means it's quadratic, essentially. I'll leave you with a little question to think about. Will all polynomials eventually have differences that are the same? And if you can find the differences that are the same, so say you find like the 6 differences are the same, does that always mean it's a polynomial? I'll leave that up to you to think about.